Okay, so the topic of today's lecture is called delta debugging. And this is a really cool technique that is based on some fundamental computer science, but it's really adapted to debugging by computers. So this is a technique that I have used 2 or 3 times in my life, and in all of those occasions, it has been a huge benefit. So I think I want to teach it to you, and I will demonstrate. I took one of the actual use cases where I found this very useful, and I constructed a small demo, 10-minute demo based on that. So we'll look at that as well. Okay, so the problem here is debugging. You have a bug and you need to isolate it, and then of course you have to fix it. But that's a separate story. What are difficulties in debugging? One of the major difficulties is to reproduce the bug reliably. The worst bugs that you'll be facing are bugs that occur now and then, so-called Heisen bugs, the transient bugs. But let's say that you are lucky, and or maybe not quite lucky. Maybe you architected the system such that you can reproduce a large number of the bugs that you're going to run into. But typically, bugs that have not been found in testing in early stages of your program are found in production when the volume of the data, the volume of the input, essentially is very big. So what you need to do is to try to figure out a smaller version of the input that still reproduces the bug. Okay, so that's really the problem that we're going to be looking at here today. And I'm going to start with a motivating example. This is from a while ago at the beginning of the Firefox project. They had bugs in the browser, as you may expect, and some of these bugs they couldn't find, so people would find them, and they would send these bug reports to Mozilla, saying, "Look, you see this page? If I try to do this, click here, the browser crashes. Or if I try to print the page, the browser crashes." And these pages were typically big because this is what the user had. It was the actual page. So one of the things they had to do before they could actually figure out what the bug is to simplify this page. Say, okay, is there some subset of this page on which the browser crashes that still crashes the browser? Now, what's the smallest subset that has this property? So what they've done, actually, at some point they got overwhelmed with the bugs. They did some sort of crowdsourcing. They said, look, we have all of these 800 bug reports. Maybe some of them are duplicate because the browser crashes. Maybe it's the same kind of crash, but we can't tell. These pages are too big. So, so to process these bug reports, the hardest task was to minimize the input. Okay, so let's look at a specific example. So this is a rather small, actually, web page that back then, if you tried to open it from your file system or from a web server in Mozilla, in Firefox, and you try to print it, the browser would crash, would segfault and die. Okay? So there is something in here that the browser kind of completely didn't like. And it turns out it's this. Okay? As long as you have a page with a select tag, but one without a closing pair, back then, the browser would crash. And if you look carefully, there is one of these on the previous page. And it's possible that 10 users have uploaded bug reports saying the browser crashes when I try to print. And it's all for the same cause. Okay, so I'd like to minimize that input, because when you arrive here, okay, this is a lot easier to fix, as you might imagine. You kind of already know where in the code to start looking. So what would you say are other reasons why you may want to fix, to minimize bug reports?
So you can write a test later to avoid regression testing?
Excellent, excellent. In fact, I do this I do this once I have a bug and minimize it. I don't want to put the whole mess as my test. I want to write a small test. But this one select, that's a good regression test. Other reasons? I think I kind of covered some of them. So as I said, ease of communication. Once you tell somebody we have a bug, it prints if you have a select statement. That's a lot more precise statement about where the issue is. It helps. I mean, this may not be obvious. The smaller reproducing scenario, it's easier to debug. In fact, it's even conceivable that you can step with the debugger through the browser while it's processing one-line web page. You couldn't do that on a big web page. And exactly as you pointed out, small reproducing scenarios make good tests. Big reproducing scenarios are typically they cover too much. They're probably not good. And an important reason is to identify duplicates. Okay, the moment you minimize it, many of them will turn to be the same cause. Okay, so the question is, how do we do this? But before I go there, what I've discovered when I taught this in the past is that the hardest difficulty. So there's some tricks in the algorithm. Okay, so part of your brain will be focusing on understanding a tricky detail in an algorithm. But the biggest difficulty students have had in the past is imagining how would they possibly use this in their work, okay? Because they're not writing web browsers, and the other couple of examples I'm going to be giving are also somewhat, they seem removed from what you program every day. But it actually turns out there's many ways, with just a bit of imagination, there's many ways to map real-world debugging problems to this minimization. So I've listed here a few. So the general setup is that you have a program that has a bug, and you have an input that exhibits the bug. Now, the whole trick in applying delta debugging and this minimization technique we're going to look at is how do you define the input? Because that's what you'll be minimizing. If the program is a compiler, the input could be the text file that you give it to the compiler, and then the minimization problem is, if the compiler crashes on this big program, find me a two-line program on which the compiler crashes. That's the minimization problem. Example 2. You have a sorting algorithm or whatever your data processing algorithm, and you give it a bunch of data, a set of numbers, and it misbehaves, crashes, it produces an unsorted result, whatever. It does something it should not be doing. Then the question is, does it do the same thing on a smaller set of data? And what is the smallest one? What is the minimum? A similar problem, except you're getting the numbers from a database. You write some batch processing to do some aggregate computation on your database, huge database, and it misbehaves. It crashes or produces the wrong result. You never saw it crash or produce the wrong result on your unit test cases, small test cases. The question is there a small test case, small reproducing scenario in this database? What are the smallest number of rows among those many that produce the same crash? Here's another interesting one. You have a program that has lots of configuration parameters, such as a compiler, for example. And the crash occurs when you have a certain combination of the configuration parameters. You can say, fix the input, but change the configuration parameters. Okay? In some way, the configuration parameters are part of the input of your program. So think broadly about what is the input to your program. This is probably closer to your projects. You have a web service, and you notice in real use that it sometimes crashes. Okay? Well, is there one of the web requests that made it crash? Or is it a sequence of web requests that constructed an internal state that made it crash? Okay? And what is that smallest input? Okay? This is a big use case in practice. Imagine web services that get lots of traffic. How do you find among all those millions of requests the 3 that if you just replay those, you crash your web service? Actually, I use delta debugging for this particular thing in practice. A similar one, except you take the web out of the picture. You have a module, and you make a few calls to the API to the module, and the last one you make, it crashes. But it's not the last one by itself that makes it crash. It depends on a few of the others to kind of create the right scenario. Okay? So the problem is, if you have one of these situations, find the smallest subset of the input for which the program still has the same failure. Okay? I do want to point out a little, here that it's important to fix the failure and then find the input that reproduces the failure. Why? Let's look at the first example again. The compiler, the input is the source file, and the compiler crashes. Most likely, the source file on which the compiler crashes is an actual valid program in C or Java. If you start chopping the file arbitrarily, pick an arbitrary subset of that source file, most likely the compiler is gonna exit very soon. It's gonna say this is an invalid program. It's not even gonna get deep inside the part where it crashes. Okay, that is still a failure of sorts, but it's not the bug you're looking for. It's not the failure scenario you're looking for. Okay, so you're gonna say for this particular subset of the input, I don't see the failure. Is that clear? Because the word failure here is used a little bit specially. If you're looking for a crash, the compiler should crash. Just giving you a syntax error, it's not a crash. And it's not reproducing your scenario. Any questions? Okay, moving along. Okay, so in pictures, a similar story. You have an input, and the input has some structure. It's not just one monolithic thing. It's a bunch of things. Bunch of requests, a bunch of characters, bunch of data rows in the database. You give it to the code and produces some failure. And the algorithm can be applied for whatever definition of failure, crash or break an assertion failure or whatever. The question is to find what subset of that input is minimally reproducing the same failure. Minimal means that if I were to further remove more elements from the input, I wouldn't get the failure, no matter which one I remove. Okay, so that's what you're looking for. You know you cannot go any smaller than this. But again, it's important, what I said on the previous slide, it's important to realize that if you start messing with the input like this, you may produce invalid input to your code, which will make it abort before it gets to the crash you're looking for. Okay? That, for you, is a good scenario. It's not a reproducing scenario. The bad scenario is when it crashes the same way. So, just to give you a preview of where we're going, I'm going to show you a technique that in some way it's so dumb that it will try to reproduce a crash in GCC by starting to chop arbitrarily the input file with no understanding whatsoever of what's a valid C program. All it sees is characters and say, I'm going to remove the 5th one, then I'm going to remove the 7th one. Okay? And it's going to feed this to the GCC compiler, and for most of those, GCC is going to say, this is not valid input, keep trying. And after enough tries, because it's a computer, all it does well, essentially, is keep trying, it's going to come up with a valid C program that goes through the compiler and actually makes it crash. And it's actually quite amazing to see it happen in practice. And it's just a few pages of code that you have to write to keep trying like this. The question is, okay, if you have a program that's even 1,000 characters long, which is a minuscule program to make GCC crash, you can't just blindly try all the combinations of characters, because that's 2 to the 1,000. That's a lot of combination even for a small program. You have to do something smart, and that's where Delta Debugging comes in. So how would you solve this problem if somebody gave you a web page that crashes the browser, tries to find a smaller web page within it that still crashes the browser? Sure, you can think of the basic solution here. Okay, so the question is, how would you solve this minimization problem? Let's say you are the browser developer and somebody gives you a large web page that crashes the browser. And I'm asking you to find a smaller one that crashes the same way, in a fairly mechanical way. I want more people to think. This isn't. Okay, I will ask the question in a simplified form. You have a sorting algorithm that crashes, and somebody kind of whispers to you in your sleep that the crash is due to the presence of one particular number in that big array that you're sorting. If the number is there, it crashes. If the number is not there, the algorithm keeps going. How do you find which number crashes? You know what? Somewhat more efficient way than.
So we already know there's only one.
Let's say we know there's only one.
So we cut it in half and check the first.
How is that called?
Binary search.
Binary search. Okay, so delta debugging is binary search on steroids. So we start with binary search. And I assume the others who raised their hand earlier probably thought of similar things. So essentially, we cut the input in half and try to reproduce the bug. And if you can reproduce it on a smaller, I think I cannot jump a little too far. We try to reproduce the bug, and if you can reproduce the bug, we iterate on a smaller input and keep going until we find our problem input. Okay, well, it's not quite so easy in practice. This binary search works fine when you're looking for a particular number, but here we're looking for a much more complex kind of scenario, reproducing a bug. So I need to introduce some terminology and some assumptions here. Bless you. So I will be using this capital letter I to denote my inputs, or the set of input elements that we're giving to the program. And I'm going to be using this kind of fail to say that given a particular input or subset of the input, I give it to my program and it reproduces the failure I'm looking for, the crash, let's say. And I need to find the minimal reproducing input. I'll be abbreviating this as MRI on my slides, and I'll sometimes use this magenta color to kind of highlight it. And MRI, I'm going to be looking for it as a subset of I. And I'm going to try to find the minimal one, although it's not going to be mathematically provable that it's a minimum. Let's say small enough. Okay, the goal is minimal, but the algorithm will compute something that's small. Now, it turns out that there's one assumption. I'll show you two flavors of the algorithm. The simple one that all of you will get very quickly, and then the complicated one, which is the one that's used in practice. But both of them have one assumption, that if it doesn't hold, you cannot use binary search, you cannot use delta debugging. And this assumption is called monotonicity, and it says that if you have an MRI that reproduces the input, any subset of the input that contains the MRI will still reproduce the input. As long as the MRI you're looking for is in the set you're considering, you're seeing the crash. And you keep reducing the set, keeping the MRI inside until you kind of, very tightly identify.
When you say every subset of the input that contains the MRI will result in failure, is that the failure we're looking for?
Yes, we're always looking at this failure, this fail. I should maybe write here red fail, okay? And that's very important. I'm not looking for compiler or syntax error, I'm looking for the compiler crash. I want to spend a couple of slides on this monotonicity because it's really, it makes or breaks delta debugging. And it's something you have to think about when you try to apply it. I'll give you some examples of monotonicity. Let's say that you have a compiler that crashes. This should be the capital fail. It's the failure we care about. Crashes as long as this particular string of characters is in the input. Maybe when it tries to convert this to a floating point, there's some code there that makes it crash. Okay? But notice, as long as this appears in the code, so this is the MRI. Anything that contains this will make it crash. There's no way to add stuff on top of the MRI to hide the failure. Okay? That's monotonicity. In the sorting case, sorting fails as long as the input contains one negative and one positive number. Let's say this is the failure. So the MRI, or one of the MRIs, might be this, -1 and 1. And no matter how many other things you add on top of this, on the input array, it still fails. That's monotonicity. There's no way to hide the failure on this by adding more stuff to the input. Or you have, in case of a web service, there's one request that crashes your service. And if there are other requests before it, it'll still crash the service. This is monotonicity. Now, why is this important? You will see actually in very completely when you describe the algorithm why this becomes important. But conceptually, as you're manipulating your input by cutting it in halves and finding subsets of it, you want to know that there's no way you will mask the failure by somehow constructing something around it that prevents the failure from showing up. Okay, because this will allow you to know in which of the two halves to go. The worst the worst that can happen when this is not true is you cut the input in half, and then you can't see the failure either left or the right side. Then you don't know which way to go. So that's why monotonicity is important. But I'll get back to this. Any comments or questions about this monotonicity? So I got feedback that I should give you a little bit more time to understand the question, or even think. Okay, no questions. Can you think of an example of non-monotonicity? You only understand the concept if you understand both when it holds and when it doesn't.
The whole idea is like independent of any other input or dependent. So if it's non-monotonicity, it means that you have other inputs that come in certain sequence in order for it to happen, right?
Yes, that's related. But can you think of an example where this would?
Only when you make a certain two requests in a certain order, only then it crashes.
But that's not okay. You're saying the scenario is you need to have these two requests one after the other. This is not necessarily lack of monotonicity. All it says is that MRI is of size 2. But because if these two in order crash, monotonicity means no matter how many other requests are added anywhere, these two will still crash it. There's no way I could add a request that suddenly masks, makes these two requests not crash.
So if, okay, I see what you're saying. So if you have another request that is not one of those two in the middle, it will not crash.
Yes, that's non-monotonic. It hides the failure.
Okay.
Yeah.
I was going to say if it depends on the state of something else.
Yes, so for example?
Like let's say there's like a browser in like an idle state, and if you were to call a GET request when it's in that idle state, it wouldn't crash. But then if it was in like a different state, I don't know, like an empty state or something, and you call a GET request, it wouldn't crash.
Okay, that's reasonable, but to use delta debugging, you have to explain everything in terms of input. So you have to think of the input being how you bring the browser in that state. So you have, let's say, a command that makes the browser idle or not idle. Then the MRI is the command of making it idle and then GET request. So it's still not it's still monotonic.
Say a method uses only like the first 5 inputs, and like say like 7 makes it crash. But if you have like 5 numbers before 7, then it won't crash. So 7 would be the MRI.
Yeah. So this is the way to actually think about it. If 7 is there, it crashes. But if there's something else, it doesn't crash, even though 7 is still there. That's non-monotonicity because 7 by itself crashes, but if you add stuff, it kind of hides the crash. There was some hand here. Okay, so I have my own a couple of examples, similar to what we had before. Let's say that the compiler crashes if this appears in the code, except if this other floating point number also appears. All right, strange bug, but just for example of non-monotonicity. So this is the MRI. If you give just this, it crashes. But if you give this program, it suddenly doesn't crash. Okay? And because this hides the bug, it prevents you from knowing that you should recurse and keep searching for it, because it looks like the bug is not there anymore, because it's hidden. It's masked by this other stuff. Back to sorting. Okay? Sorting fails if the input contains -1 and there are an even number of elements in the array. So one of the MRIs is this array, because -1 is there and there's an even number of elements. But this one contains the MRI and suddenly doesn't show the crash. And because of this, you try this, you don't see the crash, you don't know. Maybe the bug is there and it's hidden because of non-monotonicity, or it's somewhere else, so you have to look somewhere else. Okay? This is very important. Have questions?
You said that there are even number of elements, but here -1, 0, 1, it has all number of elements.
That's exactly right. So this crashes. This doesn't crash because it's odd. It's odd number of elements.
Oh.
And that's the problem, that the MRI is hidden in there, but when I execute this, I don't see the crash.
So we don't need to satisfy the even. So that if it fails only when it not only contain -1 and there are even number of elements.
Yes.
Only these two.
So this fails, this does not fail.
Right.
Okay? And that's the problem. That's the lack of monotonicity. Because this contains the reproducing scenario, but it's masked by the presence of additional input. Okay? This is very important because you start with a failure on a big input. You cut it in half. And you want to know that if the MRI is in this half, it's going to show. It's going to fail, independent of what else is around it. Same for the right side. If you don't have monotonicity, it's possible that the MRI is in the first half, you cut it to the first half, and suddenly it doesn't fail. Because it's not monotonic, there's something in there that makes it high, the failure. And then you don't know. You can't continue binary search, essentially. Okay? So let's, I kind of introduced to you this very important assumption. And in the past, I had much less material on monotonicity, and students were kind of confused. I hope you kind of got it now. So let's assume that we have monotonicity, and just to simplify matters, I'm going to make another assumption, but this is a simplifying assumption. It's one we're going to remove in the second half of the lecture. But for now, let's assume that the MRI is of size 1. We're looking for one particular input element, not a combination of input elements, but just one. So for example, have a server, and there's one request that crashes the server. Or let's say sorting fails if 0 is part of your data set. Okay? So the MRI is just array 0, and it's monotonic because as long as 0 is there, it's going to crash no matter what else is there. Okay? This is just pure binary search. With the assumption that what you're looking for is a singleton, is a single element, and there's monotonicity. It's just pure binary search. So if the input I results in failure, we cut it in half. We try the first half. If the first half results in failure, we keep searching in the first half. Otherwise, we continue in the second half. So let me illustrate this algorithm a different way. Let's say that this is our input. It has 8 elements of whatever, requests, API calls, characters in a source file, you name it. And in my examples, I'm going to show the example with the MRI highlighted in magenta. But keep in mind, delta debugging does not know which one it is. The goal is to find that 7, to discover that 7 is the culprit. Okay? We give everything to delta debugging, and we observe the failure. And this is the starting point, the premise. We have a crash with this input. Now we're going to start chopping the input. We take the first half, and delta debugging runs this, and it's not going to see the failure because we see the MRI is not in there. It's not going to see the failure. So it does the second half, and because the MRI is there, and because this failure is monotonic, meaning that 5, 6, and 8 cannot mask the failure, it's going to see a failure. And then it starts digging down in here. 5, 6, no. 7, 8, yes. So it keeps going down. 7 fails. It's a singleton. This must be it. There's no way in searching because smaller than 7 cannot be. Smaller than 1 element cannot be. Okay, this is pure delta debugging, but it's important to realize it only works because of monotonicity. Because you're not just searching for a number in a sorted array. You're searching for a scenario that something crashes on a particular situation. Well, let me now actually go into the algorithm. So I believe you understand the algorithm, but I want to actually write it down because this is going to help us once we go to the more complex algorithm. For more complex algorithm, just doing by examples doesn't fully convey it. You have to actually see it written down. It fits on one page, actually, as you might expect for binary search. The way I like to design these algorithms and write them down, especially if they have some tricky parts, this one doesn't quite, but the next version will. I like to think of what is my invariant? What is guaranteed to be true when I invoke this function, and what I expect to be true when I exit from this function? Okay? And if you have done interview questions of quick sort and that kind of stuff, that's where thinking like this is very helpful. Otherwise, you're going to be off by 1. You're going to miss something. So I'm going to write a function called dd for delta debugging, which takes a set of inputs, in this case n, named from I1 to In. And before I actually even write the function, I have a mental model of what this function, when do I invoke this function, in what situation, and what the expected output. I will invoke this function only if I know for a fact that I1 to In together, they produce a crash, which I write like this. I1 to In, arrow fail. And this algorithm is only guaranteed to work if our second assumption holds. That means there's exactly one of those inputs that by itself produces a crash. Okay? And the goal, dd, should return this ik. And now with that invariant in mind, I actually write. I first write the base case. And the base case is if n equals 1, then I have my element. Why is this correct? It's because of the invariant. Because I know that I1 to In produces the crash. Well, n is 1. There's only one element in there. So that must be the element that produces the crash. Right? So again, I want to stress these invariants. And this will be very important in the next algorithm. But now, let's say that the input set is more than 1. Then I chop it in half. Let's I1 be the first half of the input set. And I2 be the second half of the input set, from n over 2 plus 1 all the way to I. I'm invoking the program on this input I1, which I write like this. So this means execute the program on I1, and if you observe the failure, well, then we're lucky, because we can immediately ignore the second half of the input set. So what we do is recursively call dd on this I1, on the first half, and expect it to work. When you make a recursive call like this, check your invariant. Is it true that I1 to In over 2 results in failure, which is our invariant? Yes, we have just checked it. Okay? So we know that dd will do its job and will come back with one element, which we return. Otherwise, what do we do? Maybe this is a little bit too tedious for binary search, but it's important. What happens next?
Delta debugging on the second half.
Delta debugging on the second half, but is that correct? You have to check your invariant. You can only invoke delta debugging on the second half if you know that the second half results in failure. So you're correct. Let me just write it down for now, but I'll write it like this. Assert. This is not a check. I'm asserting, because if this is wrong, something is wrong in the algorithm. I'm asserting that I2 results in failure, and then I can invoke dd on I2. And let's now talk of why is this guaranteed to work. Why is this assertion true? All you've checked is that I1 does not result in failure. You're in the else clause. Well, so this is where it starts to get a little bit tricky. So this is I1, and this is I2. We know that this by itself does not result in failure. We know that there's one element that produces the failure. Could the element be in I1? It can't, but why?
Because you're in the else case.
Because I1 didn't fail, and we have monotonicity. Because of monotonicity, if the element were here, we would see the failure in I1. If you don't have monotonicity, it's not guaranteed. So this assertion can fail if you don't have monotonicity. And then the whole algorithm just doesn't work. Okay? So it cannot be in here, but you know it's somewhere, so it must be in here. Therefore, it makes sense to go and oh, one more thing. IK must be in here, and because of monotonicity, I2 will fail. Now, for safety, you can actually run the program on I2 and verify that it fails. It's actually probably a good thing to do in practice. It's going to slow down the process a little bit because each of these runs may take a while. Actually, in some of the test cases I'm doing, this can take a minute to run the program and see that it crashes. So it kind of slows down everything.
When you do delta debugging, do you always go in not knowing if it's monotonic or not? Because I guess you don't know exactly what the bug is. So.
Very good point, yes. When you actually use this in practice as opposed to in midterms or such, you don't know truly what the bug is. Okay? You don't know, therefore, that it's monotonic. But you have a hunch that if you only had a smaller web page, maybe you could find a bug. And in many cases, it's worth implementing this algorithm. It's not too bad. And it will, if it's monotonic, it will work. You'll find the input. Otherwise, you may find something smaller, but not necessarily minimal. Let me try to explain how that goes if it's not monotonic. So you chop the input in half. And let's say that this is your the one you're looking for, but you don't know it's there. And then you test this, and it's true the problem is not monotonic, but in this particular case, this fails. So that's good. You already chopped the input in half, and you completely forget about this. So now you chop it like this, and you test. You run your program on this input, and the program doesn't fail. Because monotonicity shows up now. Monotonicity shows up whenever it wants, right? So no failure here. You try it here, no failure here. Okay? The best you can do is say, well, I cannot go faster than this. So I made some progress, but I can't promise that I found the smallest one. And so that's how it's going to work. It'll help you. It just won't be guaranteeing to find the smallest input. So it actually works better than you expect most often in practice. Okay, what I'm going to do next, after the break, I'm going to show you delta debugging not on slides like this, but in a real situation where I actually use it in practice. Okay, that's going to take about 10 minutes after the break. Back to delta debugging. I have 3 slides where I'm describing a scenario where I scratch my head how to debug a very difficult problem, and then I use delta debugging, and I'm going to show you a little video with it. What I had to do a few years ago for Conviva is to write a obfuscated minifier for Lua. How many of you know what a minifier is for JavaScript? Okay, I expected more people. So when you distribute JavaScript, very often you run this program on the JavaScript that compresses it by renaming all your identifiers to very short identifiers. And this makes the whole program both smaller, and it also acts as an obfuscator because it's harder for people to actually understand what your code does. Because in JavaScript, you distribute code in source form, so you don't want necessarily to spill out all of your secrets, although they're all in there. Make it okay. So we had to write the same for Lua for very similar reasons. Conviva was writing code that contained some things that we didn't want to make to show publicly. So I wrote, because Lua, it's not such a widely used language, it didn't have a minifier. By the way, do you know what Lua is? Probably you You do? Okay, cool. It's one of the smallest languages out there, and it has a feel of like Python or Ruby, but it's really, really small. The interpreter is just 300 lines, and the goal for the language is to embed into other systems. For example, Apache has a Lua interpreter. Nginx has a Lua interpreter. Many of the distributed systems servers that run the internet infrastructure have a Lua interpreter in there, because sometimes there's only so much you can configure in an Nginx by using configuration files. Sometimes you want to go in there and add some code with conditionals and a little loop that makes you do something else. The Redis database, do you know about Redis? It's one of the NoSQL databases, has a Lua interpreter, which allows you to upload the little program into the database to really scan the database very fast, as opposed to you doing it from outside. So many games, tens of games, have Lua interpreters in which people write new characters and new behaviors. Okay, so this is what Lua is. For Conviva, it was in the context of an Xbox 360 project, which again is configurable by Lua. Okay, so back to the problem. I had to write this obfuscator. The obfuscator would find identifiers and shrink them to 1 character or 2 characters, making the result extremely hard to understand and follow. And it would remove spaces, but the goal is to do this transformation without changing the behavior of the program. We want the program to run exactly as before. Okay, here's an example. This is clear code for Lua. Local function, these are keywords. Incomplete is an identifier. MSG, message, is the name of a parameter, another identifier. Ender is an identifier. If is a keyword. You cannot rename keywords, obviously, but all of the identifiers become some very short things. Spaces get munched together, so pretty quickly you lose the sense of what's happening there. Okay, so going from here to here is the goal of the obfuscator. And now, if you have a bug in the obfuscator, what happens is the common bug that I had several times, it was mistakenly renaming an identifier it should not rename. Imagine if I take this if and I rename it into blah blah here. Of course, this is not going to run anymore, because if is a keyword, has special meaning. Identifiers you can change. Okay, so this is the common bug that I had, and the way you see this bug is actually pretty nasty. You take this big program, you put it through your obfuscator, you get another big program, but then this time an ugly program, and one word in there is renamed. One word in thousands and thousands of words. And you run this, and if the execution gets there, it starts to crash. And it produces a stack trace with function names that don't make any sense. Okay? You try to debug, to find out where in this execution you actually hit the word. It's a pain. So when I had this bug, I tracked one of them by hand, painful, a day-long thing. Okay? And I discovered, oh, I forgot to tell my obfuscator not to rename this word. And I'm not talking just keywords, which are a handful. I'm talking names of important library functions, like write, like read, who knows. And I just did my best to come up with all those names, but I missed a few. Okay? So can you see how you would use delta debugging for this? This is not easy. But I want to teach you delta debugging. It's only useful if you can find applications for it. Applications which don't yell at you, delta debugging, debugging with delta debugging. No. You have to figure it out. So let me go on and I'll show you. Okay, so this is how it's going to work. So I knew delta debugging, and after spending the day searching for this word, so okay, can I use the computer to search for that? Because what I did is fairly mechanical. And first, I'm getting my first crash. I obfuscate the program optimistically, thinking everything is fine. I run it, and it crashes. Then immediately, I say, well, this is a crash due to a bug in the original program or a crash due to the obfuscator. Well, you can test that. You can take the program unobfuscated and run it on the same input and see if it still crashes, you pass the bug on to the developer. Otherwise, it's my bug. So let's say the program doesn't crash when obfuscation is off and crashes when obfuscation is on. And I'm hypothesizing that it's one word, or maybe two, that I mistakenly renamed. So the assumption is that one of the identifiers, when it's obfuscated, results in failure. It's just an assumption. I have no idea what the bug really is. But it's worth my time to actually try delta debugging. But for this, and this is very important, I had to change the obfuscator to have the option to control which identifiers it obfuscates and which not. And you wouldn't think of that when you first write an obfuscator. You wouldn't think that you would ever need that feature to give it, say, from A to M, obfuscate, from M to Z, don't. That's not part of the use case that this program normally has. But I had to go in and add that feature, and it was a little bit of coding. And with that feature, I can control from the outside which range of identifiers gets obfuscated and which not. And then I wrote delta debugging little tool in Python that just does the binary search, passing in ever narrow ranges to this program. So what I've done this time, so I assume you have installed Lua as described in the instruction for this lecture. Let's try it out. So if you just run Lua, the Lua interpreter, you'll get this prompt. And you can actually write little programs and execute them from the command line using this -e option. For example, we're going to write a simple program that defines a local variable v, initialized to 1 plus 3, that is 4. And then we're going to print out to the console, which you do with io.write, the result of multiplying v by 3. Okay, so this little program declares a variable and does a couple of arithmetic operations and then prints the result. And surprise, you get 12. Okay, so let's look now at the actual Lua interpreter. So let's look at the more interesting Lua program now. So what I have here actually is a Lua program. It's a 360-line Lua program whose purpose is actually to read and interpret and execute Lua programs itself. So it's a Lua interpreter. Now, the real Lua interpreter is written in the C programming language, and that's what I have on my machine using Homebrew. This one, it's really a demonstration of Lua to write a Lua interpreter itself. Okay, so this program runs Lua programs, and it's very small. It's only 316 lines, which means Lua is such a popular for embedding in other systems. And let's now try to this Lua interpreter. So we invoke the built-in Lua interpreter, the one written in C, and we give it the actual Lua program. We tell it to read the Lua program for this myLuaInt.Lua. And then we pass on the Lua program to be interpreted. And I'm going to copy the exact same program from before. Okay. So now if we run this, we also get 12. So what happens is the built-in Lua interpreter reads and executes this Lua interpreter written in Lua, and it passes to it the Lua program that results in printing 12. So we're going to demonstrate delta debugging for the purpose of debugging an obfuscator for Lua. We're going to apply the obfuscator to the Lua interpreter, myLuaInt.Lua, and because there's a bug in the obfuscator, it's going to produce an interpreter that doesn't quite run correctly. And it's going to fail when we run this exact program. Let's look a little bit at the obfuscator. So the obfuscator is implemented in several files, and in one of the files there's a list of the identifiers that are reserved, and the obfuscator should not rename, such as self or module or require. These are the keywords of Lua. And I have planted a bug in this obfuscator, and namely I have removed the select reserved word from this list.
which means that when the obfuscator encounters the word select, it's going to rename it, not knowing that it's a reserved word. And that is the bug. In order to run the Delta debugger, I have first written what is called a harness, which is a set of scripts that execute both the obfuscator and then the obfuscated program, the buggy program, on a variety of scenarios to try to reproduce the bug. So I have done this in the form of a make file with several entry points. So one is make build, which by default is going to build an obfuscated version of the Lua interpreter, and is going to put it in this subdirectory build. If we call make build as I just did without any arguments, it's simply going to copy an unobfuscated interpreter. I have also written a run test entry point, which you can use to invoke the built Lua interpreter on the program that we have seen before, and collect the output in this test out, and then comparing the output, which should be 12, with the expected output. If the expected output is 12, run test returns success. Okay? Let's see what happens now if we actually build an obfuscated version of the Lua interpreter. I'm going to still use make build. I'm going to pass this obfuscate equal 1 to invoke the obfuscator. So now you can see that this took a little bit longer, and it produced in the same directory an obfuscated Lua interpreter. Let me show it to you. Okay, this is the output of the obfuscator, and if you can see, we can recognize some of the keywords if and then, and these are among the words that we told the obfuscator not to touch. So it left them alone. But everything else, all of these identifiers, they're replaced with very short names that make it very hard to understand what's going on. Furthermore, the white space has been removed, although I have left in the new lines just to make it a little bit easier to see. Normally you'd remove the new lines and then we'll just have a page of unintelligible Lua program. However, this should still be a valid Lua program, even with all this renaming. So it should still be possible to invoke this run test, which invokes the obfuscated Lua interpreter. However, in this case, we know there's a bug in the obfuscator, so it produces an interpreter that crashes. And in fact, it crashes on this very simple program that we show here. And the interesting thing is debugging an obfuscated interpreter. It's a pain. Look at the stack trace. It's all functions that you have no idea what they do, and it's very hard to go with the debugger and find out which one word in this entire interpreter has been mistakenly obfuscated. And we know it's the word select, but if you didn't plant this bug, if this was a real bug, which I actually had when I was developing the obfuscator, you wouldn't know what to do next. Okay, so here's the trick. We realized that the bug is probably that one specific identifier is renamed by the obfuscator when it shouldn't be. How do we find it? Well, we realized that there are about 80 identifiers in this program. So all we have to do is to find out which one of those should not be obfuscated. And binary search or delta debugging comes to the rescue here. We're going to have to tell this obfuscator to essentially obfuscate only certain ranges of identifiers and leave the rest alone. And then by varying the range of identifier that's obfuscated, we can narrow down and find the one that we care about. So I have done this by actually changing the obfuscator to make it take a command line argument that give it the range of the identifiers to obfuscate. And I can invoke this using the same make build, obfuscate equal 1, and now I'm passing another argument, obfuscate args, obfuscate range from A to M. Let's say we only identify the identifiers that start that are between A and M alphabetically. This is going to build an obfuscated identifier. Let's try to look at it. So if you look at it, you see now some identifiers have been obfuscated, like this R6. But this one, status has not MSG has not, because we told it that only something that's alphabetically between A and M should be obfuscated. Okay? And we know that the one we care about is select, so select should not have been obfuscated here. And in fact, if you run the test succeeds. However, if you now obfuscate from M to Z, which includes the one we should not obfuscate, we build the obfuscated identifier, we run the test, and it fails. Okay? So what delta debugging is going to do, it's going to vary the range of identifiers that's obfuscated, try to narrow down to the one that we care about. And I've implemented this in a Python script, which is delta debug. And it's actually a rather small script that implements a simple version of the delta debugging binary search. And you can invoke it by simply calling delta debug. And delta debug, this script, will actually invoke make to build the obfuscated interpreter, and then we'll invoke make run test to run the test, and depending on the outcome of the test, it will continue the search. Okay, so let's run it, and you can see it making it progress. It's a little bit fast here going about, but look, good news, it finished by narrowing down with select. So select is the identifier that should not be obfuscated. Let's look through the history of this run. I'm scrolling back and I'm seeing all of the attempts that delta debugging has done to narrow down the identifier that causes the problem, and occasionally you can see it runs into crashes. Let's start from here, for example. At this stage, delta debugging has narrowed down the search to 39 identifiers from IO std out to X. Somewhere in there is our problem. So it first tries the first half of the range, that's 20 identifiers, and that's from IO std out to push line, and it runs the test, and the test succeeds, which means the identifier is not in that range. Then it's trying the second half of that range, that's from read to X, and indeed, because we know select is among those, it crashes. So, which means that it continues the search within the range read to X. And this way, in about 10 attempts, it actually narrows down to select. I could not have done it without delta debugging.
So the assumption that we use so far is that the MRI is of size 1. So essentially, if the two halves together result in failure, that MRI, it's either in the first half or the second half, because it's of size 1. It has to be fully inside I1 or I2. If it's inside I1 is going to fail. If it's inside I2 is going to fail, and I1 is not going to fail. So these are the only two cases to worry about if you have monotonicity and MRI of size 1. But if MRI is larger than 1, there's another case you need to deal with. And that's where delta debugging is really special. Okay, there are some serious cases when this happens. For example, a sorting function fails if the input contains both negative and positive numbers. There's no way with an MRI of size 1 to satisfy this. Okay, so the smallest MRI is going to have size 2. If you make 2 HTTP requests to delete the shopping cart, the second one fails. This is a reasonable bug. Trying to delete the already deleted shopping cart fails. You cannot reproduce this with just one HTTP request. You need at least 2. A compiler crash, typically you cannot reproduce with a 1-character source line. You have to have at least a semblance of a program in there, so it's going to be an MRI of size more than 1. So the point is that in general, we need to really remove this simplifying assumption. We need to face it. And that's where it becomes different than binary search, and it becomes interesting. Okay, so let's look at and this is where, I mean, I realize this is towards the end of the lecture, but this is where it's hard. Okay, so try to pump up your brain a little bit. Okay, so we're going to start like before. We partition the input into 2 halves, I1 and I2. And if I1 fails, we're lucky. We don't care what happens to I2. We'll recurse in there. We already know that the failure is within I1. If I2 fails, we recurse inside I2. But now we have a third possibility that before it wasn't possible. We have that both I1 and I2 do not fail. Okay? And this happens because if the MRI is of size more than 1, if MRI is of size more than 1, it is possible, so let's say the MRI involves this and this. These two have to appear for the crash. The moment you cut it in half, this won't fail because you need both of them. In other words, maybe you cut the C program in half, this doesn't even compile, so it's not going to crash the compiler. This doesn't compile by itself. You need something from here with something from here. Well, how do you do this? Okay. So essentially, the failure must be a combination of elements from I1 and I2. I'll demonstrate it for you on an example. Okay. So let's say that this is the configuration, 8 input elements, and 3, 5, and 7, as long as they are all together in the input, you see the crash. If any of them is missing, you don't see the crash. Okay? So perhaps 3, 5, and 7 is the minimal valid C program included in this. So you're going to start by, you take the first half, it's not going to crash because 5 and 7 are missing. Take the second half, it's not going to crash because 3 is missing. At this point, you know that you need something from here, something from the first 4, and something from the second 4. Okay? You don't even know that the MRI is of size 3 or 4 or 2. You don't know that. So this situation is called interference, when you get lack of failure on both halves. Okay, so we need a combination. And this is, now comes actually the big idea of delta debugging. The idea is that we know that we need something from the second half. We're going to search for that something in the second half. But we know that that something only crashes if something from the first half is there. We don't know which one. So we keep the entire first half, and we start doing binary search on the second half. And throughout, we'll just keep the first half there, not knowing what's important from it. We just try to narrow down what in the second half is important. Okay? So looking at the second half, cut it in 2, 5 and 6, we know that this won't crash because 7 is missing. Okay, we try the second half, 7, 8, but keeping the first half with us. So 7, 8 is not going to crash because 5 is missing. We have another interference. Now we know the following. Something from 1, 2, 3, 4 must be present. Something from 5, 6 must be present. And something from 7, 8 must be present. Because if that weren't true, if in this 5, 6, 7, 8, the entire MRI was here, then this would crash. Because it would have the entire MRI plus the entire first half. This is crucial. Okay? So what do we do next? The same thing over again. We know that something from here, something from here, something from here. We're going to search what among 7, 8 we need. But we know that to make it crash, we need to keep the rest. So we're going to keep 1, 2, 3, 4, 5, 6, not knowing what is important there, and we're going to search among 7, 8. So we pick 7, and bingo, failure. Okay? So it looks like we have only reduced the size by 1, because we removed 8. But we know a lot more. We know that 7 must be part of the MRI, because something among 7, 8 had to be part of the MRI. We know that something in 5, 6 must be, and something in 1, 2, 3, 4. Okay? And then we keep going. We keep the 7, and we now search in 5, 6. We keep all of this, because something in here we know must be present. We keep the 7, because we found it. And we search in 5, 6. We do 5, it fails. So we know it was 5 among 5, 6. And then we keep searching in 1, 2, 3, 4, keeping 5 and 7. 1, 2 doesn't fail. 3, 4 fails. So it starts to make more and more rapid progress now, because it actually knows part of the MRI. By the time you get to this, you have them all. Okay. Yes?
Shouldn't we also check 6 and 8? Because they could be, like 5 and 6 could both be area thing.
No, we don't need to check 6 and 8 because after this stage, we know that something in here, plus something in here, plus something in here. Okay? And the moment you found that in here, all you need is 7, along with everything else crashes, there's no point in bringing 8. You forget about it at this point. Because you have, in fact, a failing scenario that doesn't include 8.
Oh, I see.
Once you get here, you have a failing scenario that doesn't include 6, so you forget about 6 and 8. And keep going like this. Keep narrowing down smaller and smaller. Right. That's a question in the back.
How do you know that 8 doesn't also cause failure?
It is possible that the bug is more tedious and either 7 or 8 cause the failure. But we don't care. As long as we found 7, that's good enough for us. It's as small as it gets. There might be multiple minimal reproducing inputs. All you need is 1. Okay? There may be several ways to make it fail with an input of size 3, but any input of size 3 is going to be just as good. Now, you're going to fix the bug that produces a crash with this input, and maybe you run it again and see that it still crashes. Well, maybe there's a second bug in there, and you keep doing this again. But for the first try, you did as well as you could. Okay? So,
okay, so let's now try to turn this example into an actual algorithm. So the situation that we have is we have the two halves together result in failure, but either half by itself does not show the failure. So we know that we need some elements of I1 and some elements of I2 to create the failures. And here's the trick. The trick is that we keep I1 constant, and we find the minimal subset of I2, let's call it M2, such that along with I1 results in failure. Okay? So we keep I1 the same, and we try to find within I2 what is the minimal part of I2 that's needed in the combination. And we know that all elements in M2 are necessary with failure, but we know that they are not sufficient. They need to be along with some elements from I1. And next, we're going to search which elements in I1 are needed. So, next step is we know that I1 plus M2 fails, which is what we have just discovered. And now we search within I1, find the minimal element M1 in I1, such that M1 plus M2 results in failure. And therefore, it means that everything in M1 is needed and everything in M2 is needed. So therefore, together, they're the minimal reproducing input. Okay, so this is let's try to turn this in. Let's look at another example of how this works. This is very similar to the motivating example with a web page that crashed Firefox that we had before. So here the initial input is this shown here on the right side here, where select size equal 5, and this is going to crash because it's a select element that does not have a terminating tag. So I'm showing in magenta the minimal reproducing input, which is just select by itself. So the size equal 5 attribute is not part of the input. And we're going to do it very dumb way. We're going to cut this HTML input in half, irrespective of whether we produce valid input or not, valid HTML or not. And we give it to the browser and try to reproduce the crash. So we start with everything and we see the crash, the failure. We then cut it in half, and as shown there, and we don't see the failure. In fact, this is not even valid HTML. Okay, we show the second half. There's no failure. Well, this is not valid HTML, but Delta Debugging doesn't know. All it knows is that there's an interference. We try the two halves. We can't see the failure. We know the failure occurs when the two halves are together. Okay, so we know that we need something from the first half and something from the second half. So we're going to keep the first half constant and search through binary search, delta debugging, in the second half. So we keep the first half constant, the select, and we bring forward half of this second half. So SIZ. This is not going to crash, not valid HTML. We try with the second half. This is going to fail because now we have all of the characters that are needed for the crash, the whole select tag. Okay, so we made some progress. We know that whatever we needed from the second half, size equal 5, it's included in E equals 5 closing angle bracket. So we're going to continue searching in that E equals 5 closing second bracket. So we take the first two characters, no. The second two characters, failure. Okay, so we have narrowed down in the second half. We know that it's something among 5 closing bracket. We try 5, no. We try the closing bracket and it fails. And because now this is of size 1, this closing bracket, we know it's part of the minimal reproducing input. So what we have done so far in this first column, we have kept the first half of our original string intact. We know something is needed from there. And we have done binary search on the second half. And because this worked pretty well because it's only one element that we needed from the second half, the closing bracket. And notice how we narrowed down and found it. But now we have to continue and find what among the first half characters are needed. But we know that whatever in there is needed needs to be along with this closing bracket from the second half to reproduce the crash. So we're going to carry this closing bracket with us from now on. And we start chopping the first part, the select, into halves. So cell, this is not going to crash, and neither is ECT, not going to crash. So we have another interference. We know that we need something from cell and something from ECT. So we keep the first part the same, cell, and we start cutting down ECT. EC doesn't crash, T by itself doesn't crash. We have further interference. We now know we need something from EC and something from T to crash. So we search in T. We bring select and then T by itself, and it fails. And because it's of size 1, T, we know that that must be part of the MRI. So from now on, we're going to keep T in the closing angle bracket. And we're going to keep searching EC. Try E, doesn't crash, C doesn't crash. We try C by itself along with everything else and we find the crash, so C is part of MRI. And so we keep trying like this and we'll eventually find out, actually through quite a few trials, that all of select is needed. Okay? So I've shown you two examples of how delta debugging works with interference. Let's look at the actual algorithm. And I want to be pedantic here as well. I want to write the invariant. And this here, it's very important because this algorithm is going to turn out to have some tricky details where the algorithm, the invariant is going to be essential. Okay, so delta debugging now takes two parameters. First is some set of input I, and which is just carried along for the ride. And the second parameter is a subset in which we're going to be searching. And we know that I by itself does not fail. But I along with I1 to IN, all of that fails. We need to find the smallest subset among I1 to IN that reproduces the failure. Okay? So base case, if n equals 1, we're done because we know that something in I1, IN is needed. And if it's a size 1, it must be I1. Okay? That was the base case. Now, for the case when n is more than 1, we construct two sets of inputs to try. We take the first half of I1 to IN over half, but we try it along with all of I, because we know that something from I is needed, so we have to carry it along. And then we construct another input with all of I and the second half that we're searching in. If I1 fails, then we know that something from the first half of I1 to IN is needed, along with something from I. So we invoke recursively delta debugging on I and I1 to IN over 2. Okay? It's important at this point to verify that the invariant holds. Well, I by itself doesn't fail, and we know that from our initial assumption on DD. And we know that I, along with that second argument, fails, and that is true because of this conditional that we just tried. Okay, so that's a correct invocation of delta debugging, and it's going to return exactly what we need. Otherwise, we try the second half. If I2 fails, then we invoke delta debugging on I and the second half, and again you have to verify that the invariant holds. The interesting case is when I1 doesn't fail and I2 doesn't fail. Well, then we have an interference. We need something from the first half and something from the second half. Okay, so first we're going to invoke delta debugging to find something in the second half that we need. So the second half is IN over 2 plus 1 all the way to IN. However, you only can run that. You can only expect to find the failure on that second argument if you carry along all of I and the first half, which is I1. Okay, we know we have to check the invariant. Is it true that I1 by itself doesn't fail? Yes, it's true, because I have just verified 2 lines above. Is it true that I1 plus that entire thing fails? Well, yes, because you can verify that that is exactly the same as I plus I1 to IN, because I1 already includes the first half, and then you have the second half. So this is a correct invocation of delta debugging. And what this returns, M2, is the minimal subset of IN over 2 plus 1 to IN, that along with I1 fails. So you know that I1 plus M2 fails. Now you need to search inside I1. And you're going to search inside the first half, I1 to IN over 2. And you're going to carry along M2, which you know is what you need from the second half. And M1, the result, is going to be the minimal subset of I1 to IN over 2 that is needed for failure. So all you need to do is then put them together, and you have the minimal subset in I1 to IN. Okay? So as you see, it's very important to verify the invariant. And in fact, I have failed to do that carefully enough, and this algorithm has a bug. And it is your homework to actually understand this algorithm to the point where you can find this small bug in the algorithm. Okay? And the hint is that you should check the invariant even more carefully than I've done. Okay, so this completes the description of the more complicated version of the delta debugging algorithm. This is the version that is actually used in practice, because that simplifying assumption that we used before, it doesn't really hold. Most minimal reproducing inputs are of size more than 1. So you need to do this kind of more complex binary search. Okay, so that completes the delta debugging, and I hope you'll keep this algorithm in mind when you have hard debugging problems that are monotonic in nature, and you may want to implement delta debugging for your problem and save a lot of time for debugging.